All right. Well, hey, welcome to the second last week of class. Believe it or not, we've got this week, next week, and then final. So we're there. We still have two more chapters to talk about, but this is definitely interesting stuff. I mean, it's all been pretty interesting. But the plan today, we're going to start talking about the nucleus, the structure of the nucleus, why they stick together, what's going on when we have decay. Um, and stuff like that. So that's the plan, at least on my side. But before I go there, oh, and then we'll talk a little bit about the exam that's coming up next time, right? In terms of what it's going to be on and all that good stuff. So, but before I go there, let me turn it over to you guys. Any questions on anything? Anything you'd like to talk about?
Yeah, I have a question.
Sure. Go ahead, Bradley.
Does this quantized energy thing still hold with things like fusion?
Oh, yes.
Okay.
Yeah. In fact, when like the energy that you get from fusion and fission and stuff like that is actually pretty big compared to the quantum steps. So we end up, being a pretty high N, which when we start getting there, of course, doesn't look quantized anymore. But yeah, no, it definitely still applies.
The reason why I asked is I was thinking about, fusion going on in the star, and that seems continuous.
Hmm.
That's why I was curious. But now that I think about it, I'm sure there's so much happening at one time that it just looks continuous.
Well, and that is exactly, I mean, it's obviously discrete because like the fusion event happens. Right? When we get fusion, that's when we have two nuclei that come together and stick together, and often that leads to a release of energy, right? So, any one fusion event happens, there is a certain amount of energy that's sent out depending upon what nuclei are fusing together. Um, but I think really you hit on it, Bradley. Is there just so many fusion events that are occurring that are happening all the time, but it just makes it seem like it's continuous. But every one of them is creating just a little finite chunk of energy that is also quantized, right? There is some n for that amount of energy that just got released, but it still appears to be continuous, right? It's not like we're looking at the sun and we see it, flashing. Oh, here came some, just because there's so many that are occurring at the same time. But good question. All energy is quantized. All right. Any other questions?
Yeah, this is a little bit more meta, I guess. But before the next exam, will exam one be graded? Or I'm sorry, I just want
No,
to.
no, no. That's okay. Don't apologize. So yeah, hopefully, hopefully. I appreciate the fact that you guys have given me a lot of grace regarding that. I already don't like to grade stuff, and just with life, I'm, it's not easy. And so that's something that just keeps getting pushed off, and I do apologize. Uh, it is high on my list. It's just not so high on my list that it's been accomplished yet. So, um, yeah, no promises.
It's fine. I just wanted to like. Uh, I wanted to ask at least. Like.
Yeah, no, and it's totally fair, and it's totally fair to ask. So, please don't apologize. Uh, yeah, hopefully it'll get done here soon. All right. Anything else? No. Okay. Well, then let me go to the whiteboard and we will keep going. All right. So we're going to start talking about nuclear physics. And I know that as soon as you hear that term, you probably have something in mind, something that usually involves either really big explosions or, like energy production power plants and stuff like that. because that is one of the things, two of the things that we use nuclear physics to do. But really, nuclear physics, all this is we're going to be looking at what's going on in the nucleus. So if you think about when we started talking about the atom, and we knew that there was we'll go to the people that were doing this at the time, they knew that there was a nucleus, right? When they first went with the idea of the plum pudding model, where charge was distributed evenly, and they realized that didn't work, and it appeared that all the positive charge was located centrally, and they called that the nucleus, right? But then we kind of got wrapped up into talking about the electron, and we looked at the electron, its energy states, and how you know, like how Schrodinger's equation applied to it, what goes on when it's in a potential well, and blah, blah, blah. And so we really kind of got stuck on the electrons. And even what we were talking about last time when we were talking about conductors and insulators and things like that, it was all about the ability for electrons to move. So we've really been concentrating on the electrons, and now it's time to start going to the center. We're going to go to the nucleus. So nuclear physics is really just all about what goes on in the nucleus of an atom. All right, so let's spend a little bit of time just talking about what is in the nucleus, and I'm sure you guys know this. The nucleus is made up of two kinds of particles, and we call those nucleons. There are two nucleons. The first is the proton, and the second is the neutron. Okay, so every nucleus is made up of protons and neutrons. Now, not all of them have neutrons. A great example is hydrogen. Just plain old hydrogen has one proton. It's only got the one nucleon, so it's just got one proton. So we don't always have neutrons, but we do always have protons. There are always protons in there. And the reason being, protons, these have a positive charge. And neutrons have no charge. And so in order to balance things out, we need to have we have to have a proton for every electron, because this positive charge is actually plus E. So it's got the exact same charge as an electron, just positive. All right, so we are guaranteed we're going to have protons, and then we may or may not have neutrons. Okay, so every nucleus, we're going to assign it some numbers, and the first is the atomic number. All right, now the atomic number, we use the letter Z to represent that. And this is the number of protons in the nucleus. And what that actually does is the number of protons determines what atom we've got. Okay, and so this, I'm going to say here, determines the type of atom. So for example, if you have two protons, I don't care how many electrons you have, or sorry, neutrons you have, but if you have two protons, you have helium, period. All right, we might have different kinds of helium, but regardless, two protons means helium. Just like one proton means hydrogen. Whether or not there are neutrons involved, one proton means hydrogen. So when you look at the periodic table, remember when we were looking at the periodic table and there was a number for each of the atoms, right? Hydrogen was 1, helium was 2, lithium was 3, beryllium was 4, and so on down the line. that's actually telling you the atomic number. It's telling you the number of protons and therefore the number of electrons in a neutral, one of those atoms. Okay, so we're going to have atomic number. That's one of them. We're going to use Z for that. Now, we're also going to have what we call the neutron number. And of course, that's N for the neutron number. And this is the number of neutrons in the nucleus. So then together, we know how many neutrons and how many protons. We then also have what we call the mass number. And this is A. And A is just equal to Z plus N. Okay, so the mass number is just the total number of nucleons. We call it the mass number because the mass of the nucleus is very close to this mass number times the mass of the proton. The proton and the neutron are almost identical masses. And so the mass number, it's really easy just to say, okay, well, let's just add those together, and that's our mass. We'll see that it's not actually quite right, that the mass isn't the sum of those. So that's what these three letters are going to represent. So when we throw them around, you'll know what we're talking about. Okay, now I mentioned that the neutrons, you can have different number of neutrons. And when you have different number of neutrons, I'm going to put here atoms with different number of neutrons. They're called isotopes. All right, so for example, the hydrogen we were looking at when we were talking about the electron and doing all that wave function stuff, that was the isotope of hydrogen that has 0 neutrons. Okay, so the neutron number was N, the atomic number was 1, so the mass number was 1. But you can have hydrogens that do have neutrons. If you've ever heard of deuterium or tritium, those are, we call those heavy hydrogens because they have extra neutrons, right? And so they are isotopes of hydrogen. All right, so we're going to want to represent those different isotopes, and we're going to want to be able to describe things and say, hey, we've got, you know, we've got gold, but we've got gold with, you know, or a certain isotope of gold, right? And so the way that we're going to do this is one of two ways. If there is a specific, if we know the specific atom, we'll actually write its name or its symbol. So for example, we'll go with gold, which is AU. And if we want to talk about which isotope, we're going to put a little number up like an exponent, but in front. Okay, so this would be gold with A equals 197. Okay, so that 197, that's the mass number for gold. So if you were to look at the periodic table, I don't know, anybody know the number for gold offhand? I'm just curious. There's no reason to. But gold is 79. Okay, so every isotope of gold is going to have a Z of 79, which then in this case would tell us that N is 118. All right, so that's how we'll do this. So this would be gold 197. Similarly, we could do this. This would be lead 210. All right. Or whatever you want, right? If we wanted to talk about heavy hydrogen, we could do, say, H2. So this would be Z equals 1, N equals 1. Just so you guys know, lead, this is Z equals 82. So in this case, N would be, what, 128? It's 128. Anyway, regardless. Okay, so that's what we're going to do when we know the atomic number. If we know the atomic number, we're just going to represent it with the symbol for that atom. Okay, but we don't always know that, right? There are going to be times where we don't actually know what, anything about it, or we want to just be generic. We just want to say, hey, we've got some atom with a certain number of neutrons and protons, and right. And so when we do that, what we're going to do is we're going to go with a generic, just X. Let me fix this real quick, make some space. So if it's an unknown or generic, we're going to go, okay, so we've got X, whatever it is, right? So it's our variable atom. But up here, we're still going to put A. We're still going to put the mass number in the same spot as what we're used to when we do know what it is. Okay, so let's put an A there. And then we'll put the atomic number down here as Z. So when we do this, this is going to be our general way of representing some sort of a nucleus. So the top number is going to be its mass number, and the bottom number is going to be the atomic number. So we'll have, like, protons, you can just read right off it. That's the bottom number. And then neutrons is the difference between those two. All right, so there's our generic guy. Now, interesting thing about isotopes is that most atoms have very many different isotopes. Lots and lots and lots, with lots of different ends that make them up. But they're not all stable. All right, and in fact, most isotopes aren't stable. And what I mean by stable is them being not stable is that they want to decay. Now we'll talk about the decay processes in a little bit, but in general, isotopes aren't stable. Like, for example, gold. I think gold has like 30 some isotopes, and only one of them is stable. I know carbon's got 2 that are stable. So depending upon which guy you've got, which kind of atom you have, we have different number of stable isotopes. And in general, for them to be stable, and this is general because this isn't always true, but for the most part, for stability, meaning they're not going to decay, in general, we want N to be bigger than Z. Like if you draw a graph where your 2 axes are N and Z, what you'll see is that all of the stable isotopes, those suckers are all on one side of that line, and they're on the side of the line where n is greater than z.
It kind of surprises me that it's not greater than or equal to.
When they're low mass, they can be greater than or equal, but this isn't a hard and fast. Okay, this is not a hard and fast thing, because, for example, just take plain old hydrogen. Hydrogen, what's its N number?
0.
0. What's its Z?
1.
1. All right, but hydrogen, just plain old regular hydrogen, is very stable. So this isn't a hard and fast, and I should put, for stability, this I'm gonna put here in general, and specifically for heavy nuclei. And what does heavy mean? Well, heavy means heavy. Big A. All right. So this isn't really as big of a thing for, or stability, or I should say instability is not really as big of a deal for the lighter elements. All right. So for like hydrogen and helium and things like that, it's not as big of a deal. But when they get big, when they get heavy, they tend to be very unstable. And in fact, once you get past Z equals 83, there are no stable nuclides. They're just the nuclei are not stable anymore. And 83 is bismuth, just FYI. So once you get to bismuth and beyond, so that's your radium and uranium and things like that, they are not stable. They will eventually decay into other things. Now, they may take a long time to decay, so they may actually stay in their form for quite some time, but eventually they will decay, at least as far as we know. Okay, so that just sort of sets the table for how we're going to describe these things, what these different numbers are, and that way we kind of know what we're talking about. All right, so now that we've talked about the different kinds of isotopes, we should probably talk about why they stick together. Okay, so because here's what I want you to think about. Let's go to something nice and easy. Let's go to helium-42. I want to get away from hydrogen, just because hydrogen is like, there's nothing to hold together, right? There's a proton. Proton doesn't have to worry about holding on to anything. But what happens when we have, something slightly bigger? So let me do this. Let me erase some more here. But why do they actually stick together? All right.
I know this is a long shot, but
Sure.
For those like really large elements that we don't get to see because they're in labs, is it possible that they get large enough to see with, good like electronic equipment?
I'm going to guess, well, okay. We can see like carbon nuclei, not like with your eyes, because the wavelengths that our eyes can receive are way too large to see them, but we can see them. Like I think it might have been in the 1980s, a lab that worked for IBM back in the day actually was able to get carbon nuclei and spell out IBM with dots. All right, so they don't even have to be super large for us to be able to do that with like electron tunneling microscopes and things like that. Now, can they get big enough for us to visually see? I don't think so. I think you would have to have such an incredible large number of nucleons in them that that's not going to happen. In just a little bit, we'll talk about the size of these things. Like if they're a sphere, basically what their radius is, and you'll see how tiny they are, even with really large A. So yeah, I think that's about as best as I can answer your question there, Bradley.
Yeah, I figured it was probably unlikely, but I was just curious.
Yeah, you were hopeful, right? All right, so let's take a look at helium-4. Now I'm going to go ahead and write it as 2,4 just to kind of get us in the habit of reading this properly. So think about what that 2 is. That 2 tells us that there are 2 protons. And the 4 tells us that there are 4 nucleons. So from that, we know that we've got 2 neutrons. Okay, so helium-4 is 2 protons and 2 neutrons. All right, so let's put those guys together. So let's say that here is one of our protons. I'll put a P on it, and then here's another proton, and then we'll put on some neutrons. All right, so we've got these 4 things that are all kind of stuck together that form our nucleus. So let's just think about the forces that we've talked about so far. Gravity. Is there going to be a gravitational force here?
Yeah, probably.
Yeah, I don't think we need to say probably. There's definitely a gravitational force because these things have mass, and we know that things with mass do attract each other. And so we do know that gravity will try to hold them together. Okay, so we know that. All right. So then you think about the other force that we know, like really there's only one other force we know. We know electromagnetic force. What's the electromagnetic force going to try to do?
Drive the nucleus apart because it's made of just made of protons and neutrons, so it has a positive charge.
Yeah, and that's perfect, Jacob. It's like think about these 2 protons. Those protons are going to try to repel each other because they have like charge. And so I'm going to put here the EM force will try to break it apart. And I know what you're thinking. You're probably going, right, but there's a distance thing involved there, and it dies off with an R squared. And so as long as those protons are far enough apart, then we don't have to worry about that. And then you might even go, and look, we've got some neutral stuff in between to try to buy them a little space. Okay, well, while all of that is true, it's not nearly enough separation. It's not nearly enough distance to make it so that these things are not going to be trying to push themselves apart. So even if you just look at these 2 things, we've got gravity trying to pull them together. We've got the electromagnetic force trying to push them apart. And hopefully you guys remember that the electromagnetic force is much stronger than gravity. If you don't remember that, or if that's never been told to you, let me be the first to tell you that the electromagnetic force is much stronger than gravity. So if you have 2, say, protons, gravity's not going to be able to pull them together because the electromagnetic force is going to be pushing them apart.
Do we have to take the electron into consideration with this?
No.
Okay.
In terms of both of these things, we don't have to worry about it, because think about gravity. First of all, the electron's mass compared to these things is really, really tiny. Also, think about how far away it is compared to how close these things are to each other. Like I know we haven't really talked about how close, or the size of an atom or of a nucleus, but it's on the order of 10 to the minus 15 meters. Right, that's a fermimeter, or sorry, femtometer, which we call a Fermi. It's so small that those electrons are far enough away that you wouldn't even notice it gravitationally. In terms of the electromagnetic force, I mean, yes, that still matters in terms of the electron, but it's not really affecting the interplay between these. The electrons are just out buzzing around doing whatever the hell they are doing, right? Which means maybe they're not even near the nucleus. Like, I don't know. So when we're talking about just the nuclear structure, the electrons have nothing to do with it. They're too small, too far away to really affect the interaction between the nucleons. But that was a good question. That was definitely a good question. All right. Well, you think about the situation. We've got a weak force that's trying to hold them together, and a force that's stronger trying to break them apart, and yet they stay together. Well, that suggests that there's another force out there. And the force that actually binds these, so I'm going to put here, so the binding force for nucleons, we call this the strong force. Sometimes it's called the strong nuclear force because it's strong. It overcomes the electromagnetic repulsion, which is big, right? We know that like charges really want to repel each other. And yet in the nucleus, there is some other force that's stronger that's going to hold them together. So physicists called it the strong nuclear force. All right. Yay. You got to love things being named what they are. Now, what causes this? We'll talk a little bit more about that later in the next chapter when we talk about more about particles and particles that are even smaller than protons and neutrons and all that. But there is just some force that we call the strong nuclear force that holds these things together. All right.
I have a quick question for you.
Yeah, go for it.
Why are we talking about these things right now as particles instead of waves? Because I'm just curious if that plays a role in, this sort of thing.
Okay. So why are we still calling them particles? Because it's convenient. Because when we think about the models of these things, they are like particles. But the other thing that's maybe even more important is the size of them. Their masses are so much greater that their wavelengths, their de Broglie wavelengths, are much smaller. So do you remember de Broglie wavelength, right? He says with question mark in his voice.
Yeah.
Right. And so you look at the momentum of the particle and you use that momentum to figure out the wavelength. Okay. So when you've got a proton or a neutron, their momentums are so much greater that their wavelengths are so much smaller that they definitely don't look nearly as much like waves as electrons do. I mean, just think about it. If you were to go back, I know we haven't talked about the mass of these things, and that's because I don't actually know their relative masses. But let me, hold on, I got a book here. Let me see if I can, if it's got the orders of magnitude on these. Okay, so mass of an electron is 10 to the minus 31 kilograms. Mass of a proton is 10 to the minus 27. So you're 1,000 times greater mass. So if you kind of do the whole momentum frequency business, you end up getting your wavelength is also off by 1,000. And so think about that. I mean, if your wavelength is 1,000 times smaller, it's way less of a wave. So those are kind of the reasons why we still go ahead and call these guys particles. And I think mostly it's just convenience. Why do I still call this a particle and not a wave? Well, because it's a particle. I don't know, we always call it a particle. But obviously the wave nature of this particle that's in my hand is invisible, right? It's like super invisible. All right. Anyway, so other than my semantics calling these particles that are sticking together, just realize now that there is this strong nuclear force that is an attraction between nucleons, and it doesn't have anything to do with the charge. Okay, neutrons are attracted to neutrons with the strong nuclear force. Protons are attracted to protons. Protons are attracted to neutrons. All right, so all of them interact with each other and pull them together. But like, it's very strong, this force, but it's also very short distance force. You don't have to go very far away before that force is not really felt. Now, when we're in the distances that we're talking about with nuclei, they're close enough for us to feel this force. But you pull, say, 2 protons far enough away, they're not going to experience this strong nuclear force attraction anymore. Okay, so it's really, really, really short distance, but quite strong. Okay, so how about we get to the how big these things are? How large are nuclei? Just so that we can get an idea of what kind of size we're talking about, to try to help you put it into perspective. Now, these distances are so small that it's a little bit challenging for us to do that, right? Like, I mean, I don't know. Do you guys even really have a good understanding of what a nanometer is? I mean, I know you guys know the numbers. I know you all know that that means 10 to the minus 9.
Absurdly small.
Yeah, but can you even conceptualize what a nanometer is? And
Not
I don't
really.
mean, yeah, and I don't mean this in any kind of a derogatory anything. I mean, I can't even really conceptualize what that is, other than, like Jacob said, I mean, an incredibly small number. It's the same issue with big numbers, right? Like kilometer, yeah, I've got an idea of how long a kilometer is, you know, roughly. 10 kilometers, sure. 100 kilometers, yeah. 1,000 kilometers, a million kilometers, ugh, no idea. Right, so we have kind of the same issue going large. 10 to the 9 meters, it's 10 to the 9 meters, it's big. 10 to the minus 9 meters, it's small, right? So I'm still going to give you these numbers so you can get an idea of how big these things are, but whether or not that number actually means anything to you is quite another story. Okay, so let's just talk real quick here about the size of a nucleus. Okay, now the first thing I'm going to write up here is something that I know you're all going to kind of rebel against. But what we're going to do is we're going to assume, you always love when I say assume, we're going to assume that it's spherical. That should make you maybe not super thrilled, but we're going to assume that they're spherical just to help us with the kind of the numbers here. In reality, yeah, many are spherical-ish, but many more are much more ellipsoidal, because it's not like we actually have, say, marbles that we're packing together, right? There is some like give and take to these things, and depending upon your number of protons versus neutrons help space them out. The electromagnetic force can cause them to do weird things, but excuse me, we're going to go ahead and say that they are spherical. We're going to assume that they're spherical. And then experiments have been done to look at the radii of these spheres. And we get a formula here that R is equal to R naught times A to the 1/3. So you remember what A was? That was the mass number. So that's the total number of nucleons. So basically, as we get more nucleons, as A increases, we get a larger radius. Yeah, duh. Why is it a 1/3 power? You guys see why that has to be?
3 dimensions.
Yeah, it's the 3 dimensions. Think about the volume of a sphere, 4/3 pi r cubed. And if we're increasing the volume with these A's, our R is going to be increasing at 1/3 rate. So that's why there's that. I mean, basically it's a cube root. All right. And then R naught, R naught is approximately 1.2 times 10 to the minus 15 meters.
Was that the Bohr radius?
So this is 1.2 femtometers. It is not the Bohr radius. All right, so this isn't the Bohr radius. And in fact, we should hope that it's not. Because think about what this is. Go to hydrogen, plain old hydrogen. A is 1, so that would suggest that R is equal to R naught. So this would be the radius of the nucleus of hydrogen. Bohr's radius has to be quite a bit bigger, right? Because if this is our nucleus, R naught is just its radius. Bohr's radius has to be out here somewhere for our electron to be going around it, right? So they are not the same. But you can kind of think of this as the standard radius, or the radius of just the hydrogen nucleus. Which then, think about this. What does that suggest for the size of a proton? I mean, if a proton is just a little ball, which it's not exactly, but if it was just a little ball, that's what this radius is its radius. So a good rule of thumb for like the size of a proton, or the size of a neutron even, because they're about equivalent, is that their radii are about 1.2 femtometers. So Bohr's radius was on the order of 10 to the minus 11. So it's 1,000 times, or not that, 10,000 times bigger, which makes sense. It should be significantly larger.
It's funny that you say that. Like, it's 10,000 times larger, yet it's still, you can't see it. You know?
Yeah. I mean,
crazy to me.
I mean, okay, so think about that then. Let's just do this real quick. Suppose that the proton in a hydrogen atom is the size of a soccer ball. I think we probably all have a good idea of how large a soccer ball is, right? You can maybe visualize how holding it in your hands. So let's say that that's the proton in it. Okay, so the electron, well, so the radius of that ball would be, in this case, on the order of 10 to the minus 15 meters. So that's our scale. So you would have to go out, like, how big across is a soccer ball? Is it maybe about 30 centimeters across? Más o menos. I don't know anybody who actually knows the size of a soccer ball, but does that seem reasonable? Like 30 centimeters?
Yeah, it seems reasonable.
Okay, so
It's like 70 centimeters.
it's 70 centimeters across?
That's what it says.
Oh, that seems like that's way too big. Anyway, let's go to a nice number. Regardless, we'll go with it. It's on that order. So you would have to go to the electron. Now, this is to get to the electron. We're on the order of centimeters, right? Like tens of centimeters. Okay, so multiply that by 1,000, or by 10,000, I mean. So now we're on the order of 10,000 centimeters, which is on the order of 1,000 meters, which is on the, as a kilometer. So if you had a soccer ball, and you set a soccer ball in a field somewhere, you have to walk about 1 kilometer away to be where Bohr's radius is.
That's nuts.
Right?
It's nuts. It's what it is.
So now let's extend that a little bit. So that's an atom. That's a hydrogen atom. So then we're going to put 2 of those together with an oxygen to form a water molecule. So again, soccer ball is the nucleus, or it's a proton basically. Think about how big one water molecule is going to be. And that's just one water molecule. That doesn't take into account, well, let's put some waters together with other things, and water is a pretty basic molecule. So now let's just kind of extend that and think about your body made up of all of those ungodly large number of atoms that are all stuck together. And yet it's almost all empty space. I don't know about you, but I don't really feel like I'm empty space. Well, sometimes, but like I'm solid, but I'm really not. There's so much nothingness in me, like literally nothingness, just space. So it is pretty mind-boggling when you actually think about it, and you think about how much space there is in one of these things. Right. The next time you think you're all super important, just remember this.
That's
Okay,
not even thinking about the emptiness of space itself.
Yeah, right.
I wonder how much we would weigh if, like, it was all occupied by matter and not just empty space.
Oh, good Lord. if you could, so like take that example, we just got this like hydrogen atom, and you were able to fill up all that space with, say, the density of a proton, dude, we would be, I mean,
Yeah, it'd probably definitely cause some problems.
well, you're talking, you are a black hole at that point. Like you're going to collapse upon yourself. I think you're definitely in the neutron star kind of realm there.
It's so crazy to think about, because we think about, like, the stuff that we're made out of, like carbon and oxygen, and in chemistry we always think of those as like lighter elements, and so we never really think of them as having the capacity for the sort of things that happen in space with like black holes and neutron stars and everything like that. But yeah, no, you're probably right. It probably would, like, it would just collapse into a singularity if we were completely occupied by matter for the, like not completely occupied, but less empty space than we are, I should say.
Yeah. And I mean, to be fair, like you were talking about how we consider these things lighter, they are light. I mean, their masses are not great. But, with what you proposed of, well, let's just fill in all that space. I mean, yeah, you would have things that are, I mean, obviously they're not going to be hydrogen anymore, right? I don't even know what we would call that if we were to take a hydrogen atom and just like completely fill it with, let's just go with neutral, so neutron density material. Yeah, I have no idea what we would even call that, but that would just be, you would have an insane A number, right? Like think about it, if you had the one proton and then a bajillion neutrons, I mean, it would be really, really insane. But yeah, anyway. All right, so again, I think that thought model helps you sort of see the sizes that we're dealing with. But at the same time, it's meaningless. What is 10 to the minus 15? I don't know, really small. What's 10 to the minus 11? Well, not as small, but still really small, right? So, take it for what it is. All right. So then, think about what kind of forces we need to hold those things together, right? We're already talking about a difference on the order of 10 to the 4 meters, right? And that's just to the Bohr radius, but obviously it can be a little bit further away or closer, but 10 to 4, 10 to 5 meters. So think about how strong that that electromagnetic force is that holds the electron in, right? That electron is trapped. It is stuck to the nucleus, not like at the nucleus, but it's bound to the nucleus. But it's on the order of, again, 10 to the minus 11 meters, 10 to the minus 10 meters, somewhere in there, right? But then think about how much force actually needs to be acting on those protons that are 10 to the 4th meters closer to each other than the protons are to the electron. I mean, that strong nuclear force has to be incredibly strong, hence its name, right? To overcome that Coulomb force, that electromagnetic force, it's got to be insanely strong. Well, that's the thing that allows us to get all the energy when we break these things apart. When we actually get nuclear energy from fission and fusion and stuff like that, there's quite a bit of energy in there. So the question is, where is that energy, and how is it that we release it and all that? Well, this comes back to good old E equals mc squared. So think about that for a second. If we go back to Einstein's idea here, we know that E is equal to mc squared. And it turns out that if you look at the mass of a nucleus and you compare it to the actual masses of the neutrons and the protons individually, we see that they don't match. All right, that they don't actually meet up. They're not equal. And so what we get is what we call a mass deficit. So I'm going to put here, mass deficit occurs in nuclei.
So if you have a recorded mass and then you add up how much there should be actually, like theoretically, they don't add up. Is that what that means?
That is exactly what that means.
That's wild, but okay.
Okay. So basically, here's how this plays out. If you take the mass of the protons, so we're going to do Z times, and I'm going to call this M sub P for proton mass. And then we add to that N times the mass of the neutron, so M sub N. This doesn't actually equal the mass of the nucleus. So again, this is proton mass, and this is neutron mass. So you add up the total masses of the protons and the total masses of the neutrons, it doesn't actually equal the mass of the nucleus. And in fact, this, if you take those two, it turns out that this is less than the mass of the nucleus. Oh, no, hold on, other way around. Sorry, I wrote that the wrong way. So the total mass of the nucleus is actually less than what we would get if we add up the individual proton and neutron masses. So hence, mass deficit. We're missing some mass. All right, so what? Okay, so we're missing some mass. Well, what the hell? Where is it and what's it doing?
I have a thought.
Okay, what's your thought?
Maybe it decayed without us knowing.
Oh, okay. It actually isn't decay. Well, here's the deal. If we call this, let's say that delta M, this is the mass difference. We know that there's some energy that corresponds to that, right? From E equals mc squared. So there's some missing energy, basically. If we get, think about the energy mass conservation. You put protons and neutrons together, we get less mass. That means some of that mass has to be elsewhere. And that's the energy. And this is actually what we call the binding energy. So some of the mass gets converted into energy. And that energy is used to hold, to bind this thing together. Trippy, I know. It's definitely a weird thing, because you would think, no, if we add up all the masses, we should get the mass. But we don't. We're always off by a little bit. Now, you can think of the binding energy as how much energy we have to supply to pull them apart. Like, take whatever this nucleus is and say, all right, what if I want to take it and break it into its respective protons and neutrons? Somehow I have to add mass, right? Well, the way I add mass is by adding energy. So you can really think that this binding energy, this is the amount of energy needed to break up the nucleus.
A lot. That's my guess.
And well, and I mean, yeah, I mean, you take that times c squared, any kind of mass times c squared, because c squared is so big, it ends up being fairly significant. So the other thing that we look at is not necessarily just plain old binding energy, but we want to see what's the binding energy per nucleon. So you'll often divide it by A, just because, I mean, if you think about it, yeah, okay, I've got all this energy, I'm gonna have to split it amongst all of the individual pieces. So how much of that energy goes to each one of those things? There's sort of a sweet spot for greatest binding energy per nucleon, and it's in that kind of like iron range. When you're in like the iron, nickel, in that kind of realm, in those metal realms, those end up being the greatest binding energy per nucleon, which means those are the hardest to break apart. Something like helium, really easy. It doesn't take a lot to break apart helium, well, depending upon which isotope. Believe it or not, helium-4, the one that's 2 protons, 2 neutrons, it's actually very strong compared to other things around it, compared to other like lithiums and berylliums and hydrogens and stuff like that. But the smaller guys are a little bit easier to break apart. But then also, once you get past the irons and nickels and you get into the really heavy things, right? Like the golds, the bismuths, the uraniums, their binding energy per nucleon goes down, but they've got so many nucleons that it's still an incredible amount of energy needed to split those things all the way apart.
I have a question for you.
Sure.
Is plasma the manifestation of this in action?
I'm going to tell you, I know virtually nothing about plasma. So I'm going to not answer that question because I have no idea. I know nothing about plasmas.
Well, the reason why I asked is I know that plasma's has to have a lot of energy, so I figured maybe this is related to it.
It could very well be. I don't know the answer to that question. So, yeah, maybe check it out. Get back to us. But yeah, I'm not really sure about plasmas. I know that my son works with a guy who does plasma work up at UNR, but I don't know. I don't really know anything about it, unfortunately. All right, so we got all this energy, this pent up energy, and we want to use it. And in fact, we do use that when we talk about nuclear reactors. So let's start heading that direction. Let's talk about nuclear reactions. But before we get to just like nuclear reactions, like, the things that are producing energy, Let's start with radiation. Because radiation actually, that is a nuclear reaction. When we talk about a nuclear reaction, we're going to be talking about things that occur inside of a nucleus. So you may know the words fission and fusion, and a lot of times that's what people think of when they think reactions, nuclear reactions. Those are two nuclear reactions, but there are lots of other things that affect them as well. And so I want to start with radioactive decay. Now, I don't know what you guys know about decay, but did you know that there's more than one type of nuclear decay?
Yes, but I don't remember why.
Okay.
3 types, but just like Bradley, I don't remember
Okay.
why it's that way.
All right. So you are correct that there are actually 3 types of radioactive decay. And we'll talk about each one of them. They are conveniently named alpha, beta, and gamma decay. So that's kind of nice. All right. So 3 types. We've got alpha. Oh, that's a little fishy guy. Beta. And then gamma. All right, now each one of these releases different kinds of particles, waves, whatever you want to call them. That was for you, Bradley. All right, but they each release something slightly different. So let's start with alpha. Now, alpha decay, what happens here is that the nucleus releases what's called an alpha particle. And an alpha particle, what it really is a pair of protons and a pair of neutrons. So remember how this works. The 4 tells you the total number of nucleons. The 2 here is the number of protons. All right, so we're releasing 4 things, 2 that are protons, so the other 2 are neutrons. This is also known as helium-4. So when this decay happens, the nucleus shoots off 4 nucleons, sends off 2 protons and 2 neutrons that are stuck together. And so that's your alpha particle. All right, now before we get to the why it does this, let's think about what this does to our element. All right, when an alpha particle is released, it's going to change the element. Do you see why?
It lost 2 protons.
Yeah, we just lost 2 protons, so our atomic number went down by 2. So on the periodic table, we're going to shift 2 spots. All right, we're going to shift 2 spots down. All right, that's what's going to happen. All right, so it changes the element. And obviously it also changes the isotope, but I think more importantly, it changes the element. All right, so what ends up happening is Z goes down by 2 and A goes down by 4. So it releases an alpha particle. We now have a new element. We have a new isotope that may or may not be stable. It may also end up going through some sort of radioactive decay. It just depends on where we end up after we do that.
That
Okay.
is something I didn't know.
That it changes the element.
Yeah, I didn't know that that was a thing.
Yeah. Pretty crazy, huh? So think about all the times when you've ever heard about or read about or talked about radioactive decay, right? Like we talk about like the landfills, you know, where they put all the stuff from spent, you know, nuclear fuel and all that. That stuff, when it changes, when it goes through decay, it's no longer the same as what it was before, right? Or think about like carbon-14, right? We use carbon-14 as a way of dating things. Carbon-14, when it decays, is no longer carbon. Now, I don't know actually if carbon goes through alpha decay or goes through beta decay, because those do different things. But regardless, it does change what kind of element it is. So, all right. So here's what alpha decay is. You know, while I'm at it, before we actually get to the nuts and bolts of alpha, let me just tell you what the different ones do. Okay, so now in beta decay, the nucleus releases a beta particle. And I'm going to put here and something else. There's a surprise. There's a little bit of a bonus when we talk about beta decay, but now we're going to release a beta particle. Now, it turns out that there are two kinds of beta particles. All right, so beta can be either an electron, or it can be what we call a positron. Now, I don't know if you've ever heard of a positron, but this is also known as an anti-electron. And basically all that means is that it's an electron with positive charge. So think about the characteristics of an electron, so mass and, you know, everything else identical. It's just positive instead of negative. Okay, so I just want you to think about this for a second. So when beta decay happens, this nucleus all of a sudden sends out an electron. That should really not sit well with you.
Nah, something's got to be happening, right?
Because there are no electrons in there, right? The nucleus does not have electrons.
Oh yeah, I didn't even think about that.
And this isn't one of the electrons that's out floating around somehow gets kicked off. No. This
is it ejected from the neutron?
Okay, so I mean that is the question, is like what the, or all of a sudden a positron gets sent out? Well shit, we've never even heard of a positron, so what do you mean all of a sudden this thing is being created and kicked out? Okay, well, when we go through beta decay, we change the element again. Because depending upon which one this is, something different happens. If an electron gets sent out, what happens here is a neutron becomes a proton. Let me, I don't want to use an arrow there. Hold on a second. So when the electron is sent out, a neutron gets turned into a proton. So the neutron basically ejects an electron, and now it's like, ooh, look at me, I'm a proton. Yeah. And if a positron gets released, the opposite happens. A proton becomes a neutron. Oh boy. All right, well, again, we'll talk way more at depth about this in a second. But I want you to realize that that changes the element as well. Because either way, we're changing the number of neutrons, or sorry, number of protons. The A is staying the same, right? A is going to stay equivalent to what it was before. It's just Z goes either up one or down one. Okay, so again, this changes the element. Z either goes up one or Z goes down one. It goes up one if the electron gets sent out, and it goes down one if the positron is sent out. But I'm going to put here A stays the same. So with alpha decay, we're sending away protons and neutrons. With beta decay, we're just changing them. We're changing the nucleons, either neutron to proton or proton to neutron. Okay, so that's what happens with beta. There's a third thing that happens with beta decay that we'll talk about when we get there. But it's really kind of the same as the positron going away. It's just you don't actually emit something. We'll get there. All right, and then lastly, of course, we've got gamma decay. Now with this one, the nucleus releases a photon. So I guess it's still a particle, right? But we tend to think of this as a wave. So this photon, of course, we call that a gamma wave. And yes, I used green on purpose there.
That was my first thought.
I don't know if anybody got that, but that's the Incredible Hulk, right? Bruce Banner gets just like throttled with gamma radiation and turns into the Hulk. So anyway, so it releases a gamma wave. So basically what this is going on in terms of where this is coming from, this is coming from the release of energy by dropping from an excited state. So with gamma decay, the nucleus gets excited, it's highly energetic for some reason. And then when it drops energy level, we know that when these things drop energy level, they do release photons with a given frequency, right? And that frequency depends upon the energy drop and all that, right? But anyway, so this sends out what we call gamma waves. Now, what's nice about this, though, gamma decay does not change the element. So neither the Z nor the A change there. They both stay the same. Okay, this is just solely due to the fact that this energetic, or this nucleus was in a higher energy state and then drop back down, releases out the photon. All right, so these are all just different kinds of radiation. They all do different things, obviously. And what tends to happen is that these go in chains. Like you'll have an alpha decay that then leads to another alpha decay, which then leads to a beta decay, which, so they often work in concert and kind of in sequence. And I'll show you what we call a decay chain in a minute. I'll pull one of those up so you can see what they look like. But anyway, so these are the three different types. So let's talk a little bit about alpha. Like what's actually going on there with this shooting out of the alpha particle. All right, now, first of all, just so you know, the alpha particle, after it's sent out, changes the nucleus. So we like to have names for the two kinds of nuclei. The first one and the second one that we sent out. And so we actually call the first one, the original, we call that one the parent. And then the one that we get afterwards, we call it the daughter. I know you would think we'd call it the child, but no, it's the daughter. So, although I think it would be really cool if we did call it the child, especially now with the Mandalorian. Anyway, which completely off topic. Has anybody heard? Is there another season coming out anytime soon? Because I'd love to get my Mandalorian on.
I don't think there will be.
Like ever?
I mean, what else is there? They go back and reclaim Mandalore? I don't know.
Dude, don't do this to me.
I know I'm upset with it too, but the way it ended was just awesome.
Yeah. Although, I mean, we didn't have to have Luke come back, but whatever.
Are you joking? He definitely needed some redemption after what the Last Jedi did to him.
I guess. All right, so let's look a little bit closer at alpha. All right, so we're going to start with the parent, which was, we'll call it XZA. Now, in the process, we're going to get something new. Actually, let me not call it X, because we'll reserve X for what the original one was, the parent. But we're going to get Y. That's going to be A minus 4 and Z minus 2. And then we're going to have on that as well a helium 4. Oh, I just saw in the chat box, Victor just said baby Grogu is life. Pretty cool. All right, so like I was saying, this one we call the parent. So the X was the parent, and then the Y is the daughter. Okay, so I didn't come up with this. I know that there are a lot of times there are things that are just Bruceisms that I give you guys. No, this is forever. It's been this. So we have a parent and we have a daughter. Okay, so what's going on here? Well, it's kind of crazy, but this comes back to potential wells and potential traps and tunnel barrier and barrier tunneling. All right, so think about this alpha particle as being part of the parent nucleus, but sort of like a separate part. So we're going to think of the parent nucleus as, we've got the daughter, so I'm going to call this Y. And then there's the alpha particle. You kind of get it, see what I'm getting at here, right? So this together, that's X. So the X nucleus, the parent nucleus, kind of looks like this. Now, the alpha particle is bound to the rest of this. by the strong nuclear force. So there is potential energy that's binding it, that's holding it. And if we were to kind of look at a graph here, where this is distance, this is U. Remember I told you that that strong nuclear force is really kind of short distance lived? Well, that means that in this graph, there is going to be a place where we've got very, very, very strong potential energy that's trying to keep that alpha particle inside, right? It's that strong nuclear force. But it's going to drop off kind of quickly. And when we were talking about barrier tunneling, we saw that one of the things that was most important in terms of the ability to get through was the thickness of the barrier. Okay, well, because this one's so thin, it makes it so that that wave function is going to pass through, right? So we're going to get the kind of look for the wave function. So as we know from Schrodinger, that alpha particle is actually still inside the nucleus, right? And also outside of it. So think of the nucleus as this distance right here. Well, because of the fact that it sort of exists in both states at the same time, there is non-zero probability that when we measure it, when we look at it, it is now outside of the nucleus. And when that happens, that's when alpha decay occurs. So it's not always at the same time, right? There's some randomness to this because it's probabilistic, which remember when we talked about, nuclear decay, like in math class, and when we say, hey, we use half-life to describe it and all that, that's a kind of a long-term, expected time, but it's not like exactly, right? Like if we say the half-life of something is 100 years, it doesn't mean that in 100 years exactly half of it has decayed, right? But that's like on average, because this is completely random. The likelihood of any one nucleus going through alpha decay, even if it's the same parent, right? Even if we're looking at, let's say we're looking at 100 different lead-210 nuclei, they are all going to decay at different rates, just statistically speaking, right? So it is a random thing. We don't know exactly when it's going to happen, but it will happen. And how often it happens depends upon this barrier. So think about things that have really long half-lives, right? So let's talk about the things that have half-lives that are like millions of years. That tells you that the transmission through this barrier is very low, right? Like it's going to take many interactions with that barrier for it to finally make its way through, as opposed to something that has a much shorter half-life. I mean, just take like carbon-14, for example, right? Its half-life is like 5,000 years or something like that. It's much more likely that those alpha particles are going to make it out. So I think this is cool. I love this because this is a really, this is a very specific example of where barrier tunneling matters and where we see it. All right, so that's what's going on with alpha decay. So remember, as we do this, if you go through an alpha decay, you're going to drop 2 in your atom, in your spot on the periodic table, and your atomic mass is going to decrease by a total of 4. All right, so there's a little bit more about alpha decay. All right,
So
now,
this
go ahead.
This doesn't have anything to do with energy. It's just this is just the wave function nature of it.
No, well, it absolutely does have something to do with energy. Like another big part of the tunneling. Remember, the tunneling also matters how close you are, how energetic you are compared to the trap, the potential energy trap. And so if your nucleus is more energetic, so it's in a higher energy state, it's going to be more likely to decay. So was that the question you were getting at?
Yeah, that definitely answers it.
Okay.
It's
So,
just I've never thought about a nucleus as being in an energy state as well. I don't know why, but I haven't. I usually only reserve that for like electrons because they're in orbit around the nucleus.
Because they're the movers and the shakers, right? We always just think about that nucleus as, boring, sedentary, just sitting around, right? And it's the electron that's doing its thing, bouncing around in the cloud. But yeah, same thing. Same thing happens with the nucleus. The particles in the nucleus can get excited, and so if they are at a higher energy level, it's more likely that that parent is going to decay, send out that alpha particle, and turn into the daughter. All right, so cool with that. And the other thing about this is not everything can go through alpha decay. And that's also an energy thing as well. That the corresponding masses after the fact, remember how like we were talking about the nuclear mass doesn't match up with the mass of the individuals? Well, you have the same issue here, that the daughter nucleus, its mass and the alpha particle's mass might be such that it can't just spontaneously happen. That when pulling it apart like that actually creates things of greater mass. And that's a violation of mass energy conservation. So there's also that in the background, that not everything can go through alpha decay. It can only go through alpha decay if the parent and daughter masses are appropriate for this to be a spontaneous thing. Right? I mean, you could force it to go through alpha decay by providing the right amount of energy for ones that don't want to go through this, but not everything will go through alpha decay. So remember when I was talking about stability earlier? That's one of the things that actually gets to the stability of nuclei, is looking at those masses and looking at what would the corresponding mass be after the fact. Do the numbers add up? Because the universe isn't going to do anything just on its own that makes you go increase in energy, right? That's not how it works. That violates thermodynamics. So just be aware that not everything can go through alpha decay. Okay, so let's talk a little bit more now about beta decay. Now, beta decay, like I told you, they're really like the two types, where we send out either an electron or we send out a positron. And but I told you that there's a little bit more to it, right? I said there was something else. So let me show you the two different kinds. All right, now I'm going to go ahead and show you two specific guys that go through beta decay that illustrate both of them. So let's start with phosphorus 32. Now, phosphorus 32, when it goes through beta decay, it turns into sulfur 32. So remember how A doesn't change, because all we're doing is we're changing a neutron to a proton or vice versa. Okay, so the mass number didn't change, but the atomic number did. Okay, from phosphorus to sulfur. This is one where we send off an electron. So I'm going to write E minus to show you that that's the electron. Okay. Now, this is the case where we send out an electron, so one of the neutrons turns into a proton. So we're actually going further down the list. Like if you think about the atoms, the hydrogen's at the top, then helium, lithium, beryllium. We just went down a step. Or on the periodic table, we just went right a step in this case. Okay, but it turned out that there's also another particle that gets sent out here. And what we send out is what's called a neutrino. All right, so anyway, so this is a case where we send out an electron. Let me show you one that sends out a positron. So a really natural one of this is copper. So if we have copper 64, it turns into nickel 64. Oh, God. Let's try that again. And it sends out a positron. Okay, so we're going to always show a positron as an E plus. So it's an electron, but with a positive charge. But it also sends out a neutrino. All right, now neutrinos. First of all, these neutrinos, the two that I have written here, they're not exactly the same. And I'll get to that in a minute because there are different kinds of neutrinos. We'll actually talk a lot about the different kinds of neutrinos later in the next chapter when we talk about particles. But anyway, so neutrinos, first things first, they have neutral charge. All right, so they're neutral charge, and that's why they get the name neutrino, right? So neutrino. But they're very small, and that's where the eno comes in, right? If you ever see that suffix, that means small. So a neutrino is a small neutral particle. They are very, very low in mass. Very low. Okay, so it's virtually non-existent. But where they came up with the like how they knew that there was another particle came a little bit later. They knew about the electron or the proton or positron because you can actually see them, and I don't mean like visually see them, but you can see their effects. Like, can you think about what you would do or what you could do to actually see that a particle was either electron or a positron?
You could put them together, try to put them together.
Okay, yeah, if you were to put them together, you could have some fun.
Or you could put either one in a magnetic field and see which way it went.
Yeah, and that's how they recognize those, was by creating, by having an electromagnetic field. When these particles got released, they could look which way they move, right? Because think about it, if we set up a field so that it's pointing whichever direction, you send out something with a positive charge versus a negative charge, they're going to go opposite ways, right? So you can see that happen. So that was really easy to see. But now imagine you have a neutral thing, a neutrino, in this same field. What are you going to see?
Nothing.
You're going to see squat, right? It's not going to actually do anything. Okay, So they weren't really obvious right away, right? Like they weren't really sure what was going on. But the neutrino actually got detected later, and it really came from looking at the laws, the conservation laws. When you look at the conservation of energy and momentum, they realized that they were missing some stuff, and so they basically said, okay, well, we believe there needs to be something else here. Kind of like, you know how we talk about dark matter, right? Just sort of feels like we've got some missing mass out in the universe. We don't know exactly what it is, we haven't seen it, so we're going to call it dark matter. Same kind of thing happened with neutrinos. When beta decay happens, there's something missing. What is it? Well, we're going to go ahead and give it a name. We're going to call it a neutrino. Okay, then later they actually were able to see them through basically how they interact with other nuclei. Since they're neutral charge, they're not going to really do anything because of electromagnetic whatever, right? But they can affect the nuclei when we look at some of the other things that neutrinos do, and we'll get to that later. But anyway, so neutrinos were one of those, we think there's got to be something, and then they eventually found out that, yeah, okay, there it is. Now, just so you guys know, there is a symbol that we use for neutrinos, and that symbol is the nu. Kind of looks like a bird. Remember when you drew birds as a kid? Here's the cloud, here's the sun, here's the birds flying. Right. So it's a nu. It's the Greek letter NU. Let me rewrite that so that it doesn't look like garbage. And you can see why, right? Nu for neutrino. So we do that. Now, it turns out that with the one when we send out the positron, we get a neutrino. When we send out an electron, we get what we now call an anti-neutrino. It is it's the same as the neutrino, but it's the antiparticle of it. So it's the antimatter pair of it. So that they're very, very similar. Their difference isn't charge, but it's something else that we'll talk about later. All right, but that's the antineutrino. And the antineutrino, we show that with the nu, but with a bar over the top of it. So that's the symbol we use for an antiparticle. So that's the antineutrino. Okay, so what's going on with beta decay? Well, beta decay is really the same deal as alpha decay in terms of the fact that it's barrier tunneling. But now what we need to think about, and regardless of which one, it's kind of a similar picture. But now what we've got is, imagine we've got let's do the one where we send out an electron. So we're going to have a neutron, or sorry, yeah, so this is a neutron. But we can think of that neutron as being made up of a proton and an electron. Okay, this isn't really what's going on. This is a way to visualize it. Okay, and so that electron is bound to that proton because it's a neutron, right? But similar deal here, that there is this energy well and this energy barrier that eventually it can get past, which then shoots out the electron. And so the neutron basically changes to a proton plus the electron plus the antineutrino. Right. And so that neutrino just comes from, again, the balance sheet. And we'll talk about that more later. So beta is also very random. It's probabilistic, but we can never know exactly when it's going to occur. So, and so the same picture, you can think of the same thing with the when we send out a positron, but the positron, that's now where the proton is basically made up of a neutron and a positron, and the positron can escape sometimes and go through beta decay. All right, so that's what's happening with beta decay. And basically, it just neutrons become protons and protons become neutrons. All right, and they do it by sending out these other particles. And just like with alpha decay, not everything goes through beta decay. It's only the ones where the math lets it go from a higher energy state to a lower energy state, so that it can just naturally occur. Now, gamma, I don't know we really have to talk much about gamma decay, because we know what happens when we have something energetic that drops down, right? It releases a photon. It's just got whatever frequency that comes from that release of energy, right? But when that actually happens, is usually a byproduct of one of these other decay processes. When something goes through alpha or beta decay, it often leaves that daughter. We still use the terms parent and daughter, by the way, with beta decay, but that daughter nucleus is often excited by this breakup, right? When it emits the particle, they tend to be kind of in an excited state. So you often get a gamma decay following an alpha or a beta decay. Just sort of depends what's going on. Okay, so I want to show you guys a picture of radioactive decay, and this does come from the book, so you can actually, hold on a second here. I want to quit sharing. I got too much stuff flying around here. I can't see what I'm doing. Anyway, so you can see this in the book, and so, oh, dang it.
I have a quick question for you.
Yeah, go ahead.
With stars, do we get the full spectrum line?
What do you mean the full spectrum line?
Like the full electromagnetic spectrum, do stars emit that full thing?
You mean visible or all?
All of them. Gamma, I mean ultraviolet, obviously. Like,
Yeah,
does it the whole thing? I'm curious.
that is a very good question. I gotta think that there are frequencies that are not emitted. That there are going to be some frequencies that just aren't going to show up because they're not possible. And I'm thinking specifically small frequencies, right? Because think about how the frequencies are built. They come from the E equals HF, right? So if those energy drops, there is a smallest energy drop. That smallest energy drop is going to correspond to a smallest frequency, which is going to correspond to a largest wavelength. So there's going to be a termination on how big the wavelength can be. But in terms of the smaller wavelengths, there shouldn't be any kind of limit on that other than the natural, like, greatest energy difference that you can get from the specific elements. Like, remember when we were talking about hydrogen, we were just looking at the electron in the hydrogen, and what was it, 12 point something electron volts? That's the biggest jump that that one can do, which would lead to the greatest frequency, which would be the smallest wavelength that we would see. And so they would all have corresponding sort of ground state energy. And so the difference there would be the biggest. So I guess I've just decided that, yeah, there's going to be a limitation on what wavelengths we see from stars. I don't know. But now I feel like I'm just talking out of my butt.
No, it makes sense. I was just curious because, like, I know we're getting shrouded with, solar radiation on a daily basis, but I was just curious if, like, they were specific or it was all of them,
Yeah. No, I'm pretty sure it's going to extend to all stars, not just ours. Like, our star's not special at all. It's really kind of a boring star. We just think it's awesome because
For now,
without it, we'd be dead. So
it might get special.
yeah, it might get more interesting over time. So Jacob, looks like you were trying to say something.
Yeah. While we're on the subject of stars, why is it that like higher, like fusion reactions that produce heavier elements, like eventually they stop producing energy, right? That's the entire thing that kills stars, right?
Yep. Iron
So like,
catastrophe.
yeah. Why does that happen? Why is they cut off at iron specifically? Like, are we equipped to know that?
We'll talk about that next time.
Okay.
We're not going to get to it today, but we'll talk about it next time. All right. Well, let me go ahead. Now I've got my windows all set up here. So let me go ahead and show you this. So this comes from the book. I don't know, what, page 482, I guess, in the PDF form of it. But this is an example of a decay chart. All right. Now, what this is showing is what happens to Throntium-232. Let me make this just a little bit bigger. Get it more centered if I can actually do this without spazzing out. All right, now the way to read these charts, we've got our atomic number on the horizontal axis. So this is the number of protons. They also gave us the corresponding atom name, right? So like 80 is mercury, 88 is radon, or sorry, radium, and so on. Okay, now the vertical line axis here is our neutron number. All right, so it's the number of neutrons that we've got available. So this is showing us something that goes through both alpha decay and beta decay. So the orange arrows are alpha decay. And remember what happens with alpha is that our atomic number drops by 2 and our atomic mass drops by 4. So think about this one where we were radium-224. It now becomes radon-220. So our atomic mass dropped by 4 and we change from radium to radon. Okay, so that's how those work. Now for beta decay, remember what beta decay does. It keeps our number of nucleons the same. So our atomic mass number, the mass number stays the same, but we change our Z by 1. It either goes up 1 or it goes down 1. So with the beta decay, you can actually see beta decay arrows going either direction. Just turns out that these all point us here to the right. So here's how this starts. So we're starting with Throntium-232. Thorium-232 is radioactive. It does decay. And it decays by releasing an alpha particle. These numbers right here are your half-lives. So Thorium-232, its half-life is on the order of 10 to the 10 years. Yeah, 10 billion years. Like older than the universe kind of things, right? Now, does that mean that we haven't seen Thorium-232 decay? Nope, not at all. That just says that that's what we should expect for half of it to decay. So let's say we have a Thorium-232 that does decay. It now becomes Radium-228. Now, Radium-228 goes through a beta decay. This beta decay, since we're increasing our atomic number, that means we had a neutron turn into a proton, which means we released an electron. So this is one that releases an electron. So that nucleus releases an electron and turns into Actinium-228. Well, its half-life is about 5.76 years. So Radium-228 doesn't stay Radium-228 very long. All right, so then Actinium-228 goes through another beta decay, releasing an electron, becomes Thorium-228. So check this out. We started with Thorium and we're back to Thorium. It's a different isotope. Well, that one is also not stable. So it goes through an alpha decay, becomes Radium-224, which then becomes Radon-220, and then so on and so forth, right? So we go through a couple more, and then we end up here at Lead-212. A couple more beta decays happen, and then another alpha, and it becomes Lead-208. All right. Now, Lead-208 is a stable isotope. So this one is not going to decay. So basically, every Thorium-232 nucleus will eventually become Lead-208 through this process of decays. And every radioactive material has one of these. I think, let me just go down. I think the book has a couple more. Yeah, here's another one. So here's Uranium-238. And Uranium-238 ends up becoming Lead-206 through this process of decays. Now, you'll notice that this one is a little bit different because like when we get to this point, which is bismuth-214, sometimes bismuth-214 will go through alpha decay and sometimes it'll go through beta decay. This is one where both of those are viable in terms of the mass energy conservation, and both will happen. But what's kind of wild is that regardless of which of those happens, they end up coming back together down here at Lead-210, which then in just a slight amount of time becomes Lead-206. All right, so we have a really good idea of what all of them do. And so something that I always like to bring up when I talk about this back in like algebra and calculus and all that is that when we go through decay, it's not that the Uranium-238 goes away. It's not at all what happens. The Uranium-238 turns into something else. In this case, it immediately turns into Thorium-234, but eventually will get turned into Lead-206. So just realize that that's what's actually happening when we talk about radioactive decay, is that we're changing, right? We're changing what we are, but we're not disappearing, right? Is there a loss of mass? Yep. There's going to be a loss of mass because our energy, there has to be energy going into, you know, and alpha particles and all that. So mass is going to change, but like that nucleus is still there. it just
I
lost
have
the heat.
a question.
Sure.
When things decay, is it instantaneous or does it take time for it to, finally break apart or
Okay.
do the decay?
Okay. So the decay of any one nucleus, like if we've got nucleus X, parent X, and it becomes daughter Y and sends out, say, an alpha particle. Yeah, no, that happens. That just goes. The alpha particle gets released, and now we've got a different material. If we're going to talk about, I've got a pile of insert favorite radioactive material here, right? So insert, yeah, I've got a pile of lead-210. I've got an ingot of lead-210. The entirety of that is going to take time for it to decay into, I guess, eventually lead-206. All right. But any one nucleus that goes through that change, it's going to happen right away. So, oh, that nucleus just went, and then, oh, now that nucleus, and then, oh yeah, okay, that one went, right? And then eventually they will have all gone. So did that kind of get to your question? I think. I hope.
Yeah, kind of. I was more so touching on like the whole quantum entanglement idea, whether or not it happens faster than the speed of light. Like you have the atom and then instantaneously now you have the daughter and then whatever it's sent off.
So, all right. So is there a little bit of a time lag?
Yeah, exactly.
I
Yeah.
mean, I don't know. I don't know how to answer that actually. Like, because well, there's going to be time. It's going to take time until we would notice that it happened. But I mean, I guess it's going to be as instantaneous as anything else. You know what I mean? Like, if you wanted to talk about, like, let's say a pine cone falling from the tree. When the pine cone like disconnects from the tree, and I'm not talking about the time it takes that the wind has been blowing it or whatever for it to finally, but like that moment of disconnect, is that instantaneous?
Yeah, I would say yes.
Right? I mean, there is the moment at which there is nothing now that binds that pine cone to the tree. And I would say it's kind of the same thing here. I mean, there is that moment where now alpha particle is no longer bound to the nucleus. You know, whatever that happens to be. But yeah,
So it's more of a semantic thing, kind of.
Maybe. I really truly don't know how to answer that question.
No, it makes sense. It makes sense.
All right. Well, I think this is a good place to stop. Now we've kind of hit at the decay processes. So what we'll do, not next time, but the time after that, right? Because next time is our exam. Am I correct on that? Is that our plan?
I think so.
Plan. That's my plan. So, because I had something else I was going to do in the afternoon. So we're going to have an exam next time. That exam is going to pick up where the other one left off. The last one, we went through the relativity, right? So that was up through chapter 5. So this one's going to be on chapters 6 through, let's make it 6 through 8. Okay, so that's going to be the whole idea of wave particle duality. So that's really what chapter 6 was all about. So some of the things that led to that, like photoelectric effect, Bohr's hydrogen model, stuff like that. It will also cover Schrodinger's equations, and things like that, wave functions. So that was chapter 7, that was quantum mechanics. So, particles in the box, barrier tunneling, this, that, and the other thing. And then chapter 8, which was on just the atomic structure. So that's where we started getting at the quantum numbers, things like spin and stuff like that, exclusion principle and whatnot. Okay, so the exam on Thursday will be chapters 6 through 8. Hopefully it'll be just nice and straightforward. As you've seen, like the math, the hard part of this math is really in the wave function stuff, but I'm not going to give you anything that's really gnarly, and I don't know if I'm going to even make you solve Schrodinger's equation, because that can be a little bit much. But I definitely expect you to be able to figure out probabilities, that you normalize the wave function if you need to, right? Like the kind of the basic things, but for the most part, it's not too mathy what we've been doing. It's just kind of mind trippy, right? So anyway, so exam's going to be on Thursday. It'll be available at 4, like always. And then you'll have until 6:30 to get it uploaded to me. But then next week, we'll pick up where we left off here, and we'll talk about fission and fusion, and get to the idea of the iron catastrophe, why that happens. And then we'll wrap up this quarter talking about particles and start talking about some of the funkier things. And we'll even get to like quarks and hadrons and all that good stuff. All right, so I think that's all I've got. So I'm going to go ahead and stop our recording and wish you good luck on the exam.